clear it's going to be relevant in a lot of different paradigms, and there's a lot of excitement in the area. And partly this is because just for a long time now, the reinforcement learning paradigm has been one of the ways we think about AI, because it's just a very natural framework in which an agent interacts with a possibly unknown environment to obtain some long-term future reward. And just because of the natural setup, it's become a broad way of thinking about these interactive learning settings. So let's jump in and just get on the same page with regards to notation and what an MDP is. So a Markov decision process is this pretty natural framework for how we model an agent interacting with the world. So, we have this agent. The agent might be controlling, say, this flying drone. It's going to take an action at time t based on, say, its policy, because the agent will have a policy which is a mapping from states to actions. That action will impact the environment. The agent will observe a reward and it'll transition to the next state. And this cycle will repeat for some number of steps. Okay, so the setting where we're going to execute a policy pi to obtain a trajectory. That trajectory, you can think of this as just a sequence of state, action, reward for some number of steps, or possibly infinite horizon. And what's our objective? Let's just make life easy and work with an infinite horizon discounted objective. So our objective is to maximize a long-term future reward based on some discount factor, gamma. So gamma basically determines the effective horizon. So you can think of 1/1 minus gamma, you can think of as the effective horizon. So as gamma goes near to 1, as gamma approaches 1, we're essentially trying to plan longer into the future because the future impacts our current utility a lot more. Okay, and our objective is to find a policy, a behavioral policy that maximizes our long-term value. Okay, so that's the basic approach. And now let's think about some of the challenges we face and get on the same page. So what are the challenges in RL and controls here? So let's just look at some super simplatory example. So we have the problem of exploration, which is the environment may not be known. We have this credit assignment problem, which is that the rewards are delayed and we might not know what caused the problem, right? We might have got to this -1 reward and which action caused problems? Was it what we did here, here, or here? Okay, and on top of all of this, we've got the fact that in real applications, we're dealing with large state and action spaces. So this is this, I don't have a video right now of this, but this is this relatively recent OpenAI Rubik's Cube solving demo. Forget about the fact that it's symbolically solving the cube, because that part's easy for computers to do. It's the fact that dexterous hand manipulation is one of the most challenging robotics tasks. Okay, and here what is the state? The state is the joint angles and velocities at these actuators. It's the cube state, and the actions are the forces applied to the actuator. So this is a very some of the state variables are continuous, some are discrete. So on top of all of this, we have this cursive dimensionality. Okay, so let's all get on the same page first and think about how we think about RL, various approaches, deep RL, and contrast them to supervised learning. Okay, and because supervised learning is one of the things that has worked remarkably well in the last decade in machine learning in areas like vision, speech, natural language processing, and we're using that in these reinforcement learning settings. So let's just start from the basics and go back to the classical dynamic programming approach and how we solve this problem. Okay, so let's think of this implausible algorithm for a problem of this size, but let's take a look at what's going to happen. We're going to make this big table where, this first column, we've got states. So this would be like the joint angles, the cube configuration. Then we're going to have the action we take. So it's going to be the forces at the actuators. And the way this algorithm is going to work is we're going to start with some policy pi. We're going to define this thing called its Q function. You can think of this as a one-step look-ahead value. So what Q pi of SA means is we're in state S. We then take action A, then we follow pi. So the very first step, we deviate from our current policy. by taking A, then we follow pi. So it's kind of like looking ahead for what our value is when we deviate. Okay, and we're going to put that that number in this last column in this table. So this is this one-step look-ahead value. This table is infinite. We're going to compute that number, put it in every entry in that table. Then we're going to update the policy to be greedy with respect to this look-ahead value. Okay, so then the next policy, it's an iterative algorithm. The next policy is going to be greedy with respect to this queue, and then we go back and fill this infinite table again. It's uncountably infinite in this case. Okay, and the question now is, how do we deal with this infinite table in realistic settings? Because there's just a lot of challenges here. Okay, and the approach that we often take is to use some kind of sampling or supervised learning approach, which is we're trying to handle this by generalization. We're only going to see some entries in this table, and then we're going to try to generalize to fill in the missing entries, which is what supervised learning is very good at doing. Okay, and that's really one of the, so two of the ideas in which RL and quote unquote deep RL are different from more classical ways of thinking about these problems are that, often the model is unknown, and that's considered in various settings. And the bigger part is we're often very interested in this cursive dimensionality, where we're trying to get at generalization, because this idea has been really core for many successes in machine learning in kind of non-interactive settings. Okay, so now let's jump in and see what people tend to use in practice to get state of the art. One of the most popular methods right now, like if we have a system, we really want to get things to work, we're actually going to do gradient descent on the objective function we care about. So we're going to have this parametric policy pi theta. So we parameterize the policy in some way, and then we're going to do gradient descent on an objective function to try to directly maximize the objective function of interest. Why is this approach popular? Well, it's great for dealing with large state and action spaces because you can just parameterize this policy with some big neural network, right? So this policy is a mapping from states to actions. It's probabilistic, and you just write down some crazy neural network and then try to optimize the parameters of this network. This approach is pretty amenable to sampling. So even if you don't know the model, there's various Monte Carlo ways of estimating this gradient with rollouts in the world. So this is basically the likelihood ratio method. And finally, the aspect that I think is critical here is that these methods really directly optimize the cost function of interest. And that in machine learning more generally, we know it's a good idea to, if we have something we care about, write down the objective function and spend a lot of time doing direct optimization on that objective function. And this is clearly something that leads to, we shouldn't discount this approach. Okay, but the RL setting is different from supervised learning, and it has a number of unique challenges. And that's what we're going to focus on shortly. So let's contrast what this basic optimization approach, how it differs in the supervised learning setting, say in comparison to the reinforcement learning setting. So in the last decade or so, we've come to realize that non-convexity is largely not such a big issue in supervised learning. Like practitioners, you tell them the problem is non-convex, no one cares. They just run gradient descent with their deep network, it works really fine. And we've come to believe that the landscapes we often work with are pretty well behaved. They look like this picture here. So if you get stuck here, it's very easy to just shake the system and you'll roll away from it. But in reinforcement learning, so this is like a contour plot where we're trying to say minimize this function. So in reinforcement learning, this is not the picture in practice. Okay, so in actual reinforcement learnings, we really do have very, very flat regions where the gradient is near to zero and we're nowhere near to the reward. Okay, and I'll give you one example, a concrete example in shortly, but conceptually, think of a setting where we have a robot, we wanted to get it to stand up. Okay, and hypothetically, suppose it's a sparse reward setting where we only give the reward signal or the cost when the robot has stood up. So if you drive the system randomly, it gets no reward and no gradient signal. Okay, so, and this comes up in many different settings. So concretely, think of, so now we'll start with just a technical lemma formalizing this issue of flat gradients. Okay, so suppose we've got S states in the world, the agent's going to start here, and it gets a reward only if it gets to the rightmost state. Okay, we've got two actions going to the left and one going to the right. So if we start our system randomly, we've got a random walk with a bias going left, and it's going to basically take exponential in S number of steps before it'll hit the reward state. Okay, and what does that mean? That means that translating this into optimization, what this means is the gradient is very small, and not just that the gradient is small, that the gradient for all higher orders in spectral norm are small. So this up to basically almost order S. So this picture is, it's not just your gradient is flat, it's the second derivative is flat, the third derivative is flat. So you're in this region that you're really just stuck everywhere. Okay, and that's really not this picture we see in practice in supervised learning. What that means is, even if we had exact gradients, we might not expect the classical optimization approaches to just the classic, gradient-based local search methods to work in such problems. And that's what we're going to try to get at today. What are the ingredients to actually get these approaches to work? Because empirically, they do work quite well. But can we get any handle on what's going on with them with regards to, say, global convergence and their approximation power? Because we don't want to just solve these simple tasks like this, where there's a small number of states. We want to solve these much harder problems, and we've seen plenty of empirical successes in these harder problems. Okay, so this has kind of put us on the same page that, we've got a non-convex optimization problem. We see saddle points are very different in this RL setting than in supervised learning. And what we care about from a mathematical point of view is both issues with regard to global convergence and generalization. And that's what we'll look at today. And we'll really break things in two parts. So we'll start with the case of small state spaces. So like, think about this simple maze task in this last example. We have a relatively small number of states. And here the issues we're concerned about are curvature and non-convexity. So we're really going to try to understand what happens if we run gradient descent on these problems. And then once we understand that, we'll turn to the issue of what happens when we deal with large state spaces. Because the reason we're trying to do this is not to kind of just solve these small problems. We're looking at these gradient approaches because they're very nice in that you can easily replace your policy with some newer policy and run some optimizer on it. And that's what we ultimately want to get at, is how do we think about generalization in these settings with regards to such methods. And the hope now is we can actually get better algorithms in this process, or at least see the challenges we face. Okay, so part one is the issue of small state spaces. And we're trying to understand, do these methods converge? What are the requirements for policy gradient-based methods to converge? And in the small state space case, let's parameterize things in the simplest possible way to avoid projection. So a policy is a mapping from states to actions, but if we want to take a derivative, we want a stochastic policy. And rather than dealing with a constrained optimization problem, we constrain the policy to lie in the simplex through, say, doing projections. Let's just directly parameterize a policy in a manner which keeps it in the simplex. So how do we do that? Well, the simplest way to do that is, let's just consider the softmax parameterization, where the parameters are, so the parameters here are theta of SA. So we've got one parameter for every state action pair. And the probability of A given S is proportional to e to the theta SA. So it's clear that this policy class contains every stationary policy. And our question now is, we have this non-convex optimization problem. It's not too difficult to just look at this optimization problem where max theta of our value is starting at some state S0. And it's not too hard to see that this is non-convex in our parameters theta. Okay, so now the question is, look, do we even have global convergence? Let's forget about rates. Were this in the limit? Suppose we had an oracle that gave us exact gradients converge to the globally optimal answer. Okay, by the way, so in case I lose a sync, so sometimes like my PDF won't, it won't advance slides, so just let me know and I'll reshare my screen. Okay, so we'll start with the most basic question. Forget about rates, do we have global convergence? Okay, and to get that, we're actually gonna have to modify things slightly. So rather than considering the objective function v theta of S0, let's consider starting the agent with some distribution over starting states. Okay, so the intuition now is in this, like in this flat gradient problem I showed you with this agent wanting to go right, but if it starts randomly, it'll mostly move left. We're actually going to start the system rather than starting it at this leftmost state, start it with some distribution that has support everywhere. And the idea for doing this is that because you're starting it everywhere, hopefully it'll have some type of gradient signal because you've started it near states which have reward. So then maybe if it just acts randomly, it'll hit the reward, and then it could do some type of backward induction implicitly to get there. Okay, so what we're going to look at, so the first concept we're looking at is we're not actually doing gradient descent exactly on the start state of interest. We're going to do gradient descent on this objective function where this measure mu is smearing out the starting states. Okay, then let's look at gradient descent with an oracle that gives us exact gradients. So again, this is an abstraction because we want to understand what's going on from a fundamentalist point of view. So let's assume we can exactly get gradients. And the first result is that as long as this measure mu has full support over the state space, then for every state S, you will in the limit converge to the optimal policy. Okay, so why is this interesting? Well, it's non-convex and we have global convergence. Okay, and if you think about it, you could very well, your parameters could very well be wandering off to infinity, but you're still kind of going in the direction that's getting you to the optimal objective value. Okay, and the proof here is it's definitely detailed and it's very technical because of this issue that the right answer is out at infinity. And one of the reasons this proof is technical is the rate for this algorithm truly could be exponentially slow in the number of states and the horizon. And why is that the case? Well, it's because the softmax policy parameterization, if you think about it, as your parameter gets big, which basically means your policy is going to become near to deterministic, your gradients are going to become flat. Okay, and what could be bad is it could be flat in a region that isn't close to the right answer. Like you could charge off to one corner of the simplex, but eventually you're going to have to leave that corner and go to another corner. Okay, and that's basically the fundamental issue, that we need some way of preventing these flat gradients, but we could go deep into a corner before we head away. Okay, and somehow just shaking the system and adding noise isn't really going to fix this. But at least we have a sanity check that we do have global convergence. Okay, so let's start with the first concept to try to get at what's going on here. Okay, and one way we try to fix these issues is through regularization. Okay, so let's consider putting a barrier against the walls of the simplex. So we know eventually the optimal policy is deterministic, and that means we're eventually going to have to go into some corner, but maybe we can put some penalty lambda to push us slightly away from the corner. So it's kind of like a bias variance trade-off, but it's more of a barrier that by putting in this barrier function, we're not going to get quite exactly to the optimal policy. That depends on lambda, but we might be able to move more quickly because we've pushed ourselves away from the corner. Okay, and what's the penalty we want? This is basically, it's basically a KL penalty because it's a KL distribution to some type of uniform distribution. But you can see if you penalize by the log probabilities, you'll never want a probability near to 0. Okay, now we can do gradient descent on this, this modified objective, the surrogate objective, with this barrier function. And now we're going to set lambda as a function of our target accuracy epsilon. And what's interesting here is that we do in fact see global convergence at a polynomial rate now. Okay, and we have to set lambda as a function of epsilon, but you just run gradient descent. And again, suppose we have an oracle that gives us exact gradients, then we will get global convergence at a polynomial rate, assuming we set the learning rate and lambda appropriately. Okay, so why is this interesting and possibly relevant is, well, it's non-convex, but now we're in the realm of actually getting a polynomial iteration complexity. Okay, so we're converging. And this is something that is very relevant in practice, because in practice, people often do put penalties to try to prevent the policies from becoming deterministic too quickly. Okay, what's subtle here is that we're actually using this KL-based regularization. So this thing is equivalent to a KL penalty. And one of the things people use in practice is entropy regularization, which is a little different. And entropy regularization technically looks too weak to get a polynomial rate, but it's being used for the same type of reason, that we're trying to penalize policies from becoming too random in some way. Okay, so now we're in the land of polynomial convergence, but what's annoying is that polynomial convergence still isn't great, because remember, eventually we want to turn the tables and move to the case where we have a large or an infinite number of states. Okay, so this is problematic in that even in the case where we can get exact gradients, this convergence rate is, while at least is nice because it's not exponential time, it's poly. So it's not just poly, it has an explicit dependence on the number of states. Okay, so let's try to understand what's causing the problems. So what's causing the problems is that, well, how to modify things to avoid this flat gradient issue. What's going on is, we've got this real valued parameter space, theta, and we're using that to parameterize the simplex. And that means our gradients are really flat near the corners of the simplex, because the theta values, over here, this is where theta is going to infinity. Okay, and that means our contours are getting closer and closer together, and we're getting like very, very flat gradients. And the idea now is we're going to consider a preconditioning approach, really motivated from statistical considerations, where near the corners, let's actually try to adaptively take larger steps, because that's where a gradient is small. Let's warp the space with a preconditioner to try to take larger steps when the gradients are small. Okay, and that's really trying to make, to utilize the geometry of the problem. Okay, so this is this natural policy gradient approach, and TRPO and PPO one can really view as variants of this idea. Okay, so the idea is, let's consider the Fisher information metric of the policy. So this is, we look at the average Fisher information metric. So this is, so the Fisher metric is a metric on a probability distribution. And remember, for every state, we've got a distribution pi a given s. So a policy is really a family of probability distributions. Okay, and each of those probability distributions is gives us a metric for how to move more quickly, because the Fisher metric basically is something that tells us how indistinguishable points are. But operationally, what it's going to do is, near the corner, it's going to make distances much closer together, so we can move further. Okay, so we're going to define this metric based on the average Fisher information metric, which is averaged over the states we visit under the current policy. Okay, then we're going to do a preconditioned gradient approach, and by preconditioning, we're just going to invert this metric and follow the gradient. Okay, so it's a PSD matrix, and it's adaptive because it's a function of the current theta we're at. Okay, and it's also a function of the current S0 as well, because this expectation with respect to the states and actions we take starting from S0. Okay, so you can really think of just as a preconditioning method. We're going to try to stretch the corners out so we move more quickly. Okay, and now we can say, we can ask the question, can we actually converge more quickly by this more geometric approach to optimization? Yeah, and this is common in ML more generally with like Atom, Attograd. There's plenty of approaches which try to precondition the system to optimize more quickly. So let's look at this approach again for this simplified setting of the softmax policy class. So again, this is this policy parameterization, which is very simple, which the chance of A given S is E to the theta of SA. This natural policy gradient approach is literally just this update rule. But what's quite interesting here is that this update rule, it's exactly equivalent to the following update rule. So if we look at this update rule as a function of theta, see how it updates the policy, what we're going to see is that the way it updates the policy is we're boosting the probability of A given S by something that's exponential in this one-step look-ahead value. So we're multiplying pi of A given S by E to the eta of this Q function. Okay, and what's also interesting here is there's no dependence on S0 here. Okay, so even though this thing depends on S0 and this Fisher matrix will depend on S0, that dependence cancels out and we get this update rule which has no dependence on the objective function. Okay, and if you look at this, it's very striking because it looks a lot like this tabular approach we just discussed at the start, where if we made eta infinity, we would actually be jumping to a greedy update rule. So you can think of this as some type of interior point approach where we're softly moving toward the greedy update rule. And if we take a large step size as eta goes to infinity, then we will in fact recover that greedy update rule. Okay, but the reason this is interesting is that this soft update rule allows us to start doing things like replacing the policy with, say, neural policies. Okay, but before we take the step of looking at the case of large state spaces, because this update rule, right, this update rule makes sense even when we have other policy classes and it's widely used. Let's actually see what happens in this simplest possible case, because again, it's still non-convex, but because of this interesting connection to policy iteration, we might expect good things to happen, right? Because when eta is infinity, we're actually just jumping to a policy iteration update. Okay, so what's the convergence rate of this approach? And this is quite striking. So assuming we set the learning rate appropriately, after t updates of this, t iterations of this algorithm, again, we're going to assume we have access to exact gradients and an oracle gives us this, this Fisher metric exactly. Then after t iterations, we'll order 1 over t close to the right answer, and we depend on 1 over 1 minus gamma squared, which is this effective horizon. Okay, so what's striking about this convergence rate? Okay, so it doesn't depend on the number of states, the number of actions, or how we start the system. Like we didn't have to start with the uniform distribution. We could just start at a single state S0. And we've got this dimension-free iteration complexity. Another thing that's striking is, from an optimization perspective, these type of rates are known as fast rates, right? Because when you get rates that are like 1 over t, that is, it takes order 1 over epsilon iterations for epsilon optimality. Okay, and the slow rates are typically 1 over epsilon squared. So there's something structural in this problem that allows the rate to be improved over these settings where you get order 1 over epsilon squared convergence rate. And perhaps more surprisingly, this is non-convex and we're getting a pretty clean convergence rate. And what's quite interesting. Like this proof is worth looking at. So the asymptotic one, the first result I said, that proof is very detailed. It's not informative. The log barrier, I don't know if it's not informative. It's just, it's very asymptotic, that first result. This log barrier proof is a good bit more intuitive, and it's getting at what's going on. And this proof is remarkably clean in that somehow, even though it's non-convex, we're making a pretty interesting connection to this mirror descent style of analysis that was developed in regret minimization. And the proof techniques really go back to this paper where we're looking at a regret in an MDP setting. But somehow, even though it's non-convex, you can make these connections to multiplicative weights algorithms and a mirror descent style of analysis to get this fast convergence rate. Okay, and
that's a quick question.
Yeah, go on and go for it.
Yeah, sure. For this method, where the number of gradient steps are much reduced compared to the vanilla gradient, I'm just wondering how difficult it is to implement per step of molecular flux gradient compared to the vanilla version.
Right. So Guanan's question is, what's the per step iteration complexity of this algorithm? So for the exact approach, I would argue it's comparable, because to compute a gradient involves getting the Q pi's and matrix, you're gonna have to do matrix multiplications, and that's the same cost as matrix inversion. So in the exact case, the iteration, the computational complexity of doing each step exactly is the same. Okay, but but maybe I'll jump ahead with this question, which is what's interesting now is that because we don't have this dependence on S and A, we can start thinking about the stochastic case where we're going to try to estimate these things and what happens when there's like various approximation error. But in the exact case, it's comparable computational complexity to do each step. But the striking thing now is we can see what happens, say, for example, when we don't have the softmax policy class, because now we're in a setting where we can actually deal with this problem of a lot of states and actions. Okay, so now at least we have some hope of trying to, say, analyze a neural policy class, because we've got rid of these explicit dependencies. Okay, so, but the short answer is, for the exact case, the computation is the same.
Thank you.
Okay, so let me look at the time. I have time to do this. So let's do a, right, and that's exactly this question of what happens when we don't have this oracle. What do we do? So let me just quickly show a couple of videos to, so now when we go to, now we're gonna go to the large state space case, and what we know in practice is the starting distribution in many cases is quite important when we run a policy gradient method. And let's see why. Let me just, do you see a share screen now with some simulations there? Okay, good. So I'm gonna show you some videos now. Okay, so what I'm gonna do is we're gonna have a system that's trained to do well from one starting state. Okay, now we're gonna like perturb the system in some way and see if it can still do well. Okay, so this is a hopper. We apply some force. This thing falls over, it can't get back up. So this thing knows how to get back from one starting configuration as 0. So it solves the task just fine, but then we apply a force and it doesn't get back up. Same thing here with this little walker. It knows how to run on its own from one configuration, but if we kick it, it can't get back up because we perturbed it in some way, and it's in some region of the state space that it's just never visited before. It doesn't know what to do, and it's stuck. Okay, and this happens like all the time. Okay, and how do we fix this? Well, not just for optimization reasons, even for robustness reasons, we often start the system in lots of different configurations to try to make it robust to perturbations. Okay, and this is also what they needed to do in this OpenAI task. They wanted to be robust to perturbations, and they call this domain randomization, but they trained in all kinds of different physics configurations. But that really is, you can view it as just choosing a much richer starting configuration for optimization purposes. Okay, and now we're going to get into this issue of generalization, because sort of robustness and this measure and approximation, they're kind of two sides of the same coin. We're trying to get at a generalization when the number of states is large. And we also want to understand what's the role of the starting measure mu, because that went away from the natural policy gradient. But if you think about the sparse reward case, once we start sampling things, we're going to have some dependence on there's no way we're going to solve this the sparse reward problem if we start by driving the system randomly when we're sampling gradients. Okay, and the way we're going to fix that is think about some way of starting the system more broadly with mu, and we want to see the effect of this. And just in terms of related work, even some of the earlier work, we've understood the importance of this measure mu, going back to this conservative policy iteration method. And that measure mu is also very relevant in analyzing things like imitation learning, because that's where an expert starts us off. Okay, and so now let's jump to the case of large state spaces. And more generally, there's been a fair bit of recent work trying to understand non-convex approaches in RL and controls. So some of these statements, there's analogs in the control theoretic setting. Okay, so let me jump to back where I can write again. So now I'm gonna okay, great. So I take it you can see a screen that says part 2, right? Okay, great. So take this little break. We see that this measure mu is relevant because you can think of this as having coverage. What are the implications of that when we're dealing with large state spaces? And what is our intuitions and analysis techniques that we just developed in the small state space? How are things going to play out in richer problems? Because that's where these methods really shine. And that's where machine learning is good. It's great at generalization. Okay, so more abstractly, the types of policy classes we use in practice, they're almost always of this form. The probability of A given S is always proportional to some E to some type of energy function as a function of theta. Okay, so we saw one case where F theta of SA is just the parameter theta of SA. We're gonna briefly look at this log linear policy class where these features are known. Okay, so now the idea is hopefully we're going to have some dimension D, which is smaller than the number of states and actions. And if these features are good in some way we have yet to quantify, maybe we can deal with the curse of dimensionality, because now the number of parameters we're trying to learn is only order D as opposed to the number of states and actions. Again, this is where this feature mapping is known. And of course, another setting which is used pretty often is when F theta is a neural network. So that's where this top layer might be phi, but we're actually learning the representation. So all of these are just different classes of these energy function ways of parameterizing a policy. And rather than jumping into understanding the neural case, which you can see the paper for that, we'll take a little time to at least look at this case of log linear policies, because that already is getting at how might we handle the case of large state spaces. Okay, so in particular, we're thinking about the regime where the dimension hopefully is much, much smaller than the number of states and the number of actions. Okay, so we know the features. We have this parametric policy class where the probability of A given S is e to the theta dot phi of SA. And let's now look at this natural policy gradient update rule, because why is this update rule interesting to look at? Because we already know in terms of its iteration complexity, if we had exact gradients, it didn't depend on number of states and actions. Okay, so now what we want to do is now let's look at restricted policy parameterization and think about what's going to happen there and how we can estimate these gradients, say from samples. Okay, so let's first look at the exact case and what the equivalent update rule is, because this is the update rule. This is our update rule. Let's see what's going to happen when we look at this update rule in the space of policies. Okay, so here's an equivalent way to look at this update rule. So one way is we just update the parameters according to this, but we can see what happens to pi theta. Right, so when we do this, this is equivalent to, say, pi theta being updated. Right, so this is really theta t plus 1. This is theta t. And we update this policy. What's an equivalent way to look at how the policy changes? Okay, so this also has a very strikingly simple form. So an equivalent way to implement this update rule is take your Q functions, these kind of quote unquote one-step look-ahead values, do a linear regression to find the best fit line with your features. Okay, so the features are in R to the D. You're going to find weights that best fit this Q function. Okay, so that's a regression problem. And that regression problem is going to be under this distribution D, but this is an on-policy distribution. So what is this distribution? This is the distribution over states and actions you visit when you start at some state S0, then take action A0, then you follow the policy pi. Okay, so this is basically like an on-policy way of estimating the Qs, right? You just keep doing resets, keep doing rollouts, you get these trajectories, and then you just fit the Qs under the data you've collected. Okay, and we're going to define this W star to be the population minimizer. Okay, and I'll leave this as a homework exercise to see why this update rule is equivalent, but the claim now is that these two update rules are equivalent. Okay, so this second update rule is a two-stage procedure where first you fit W, then you say your new policy is the last policy where you multiply by e to the W star dot phi SA. And that kind of makes sense because if you think about it, it's like we're approximating Q of SA by this W star dot phi of SA for a given policy. All right, so it really is analogous to what we were doing before. And where's this regression coming from? Well, if you just look at the functional form of this F theta inverse ends up looking like a regression. Like you plug in some stuff, you see like a phi transpose object there, and this ends up looking like just straight up ordinary least squares regression. And then you plug in the update rule, and you see it's equivalent to this. And note, what's nice is you recover this tabular case, because if we make the features to be this one hot case, we exactly recover this tabular case. Okay, but what's nice now is we can think about running this algorithm in an approximate method or a sample-based approach, because this exact update rule assumes we do this regression exactly, and that is really just corresponding to this F inverse. And then we're doing this exact update rule, but we can see what happens when we use samples. Okay, and note while I'm writing the policy is being updated here, note we only keep track of theta t. We don't actually need to write down a big table of pi, because this pi, because pi a given s at time t is always proportional to e to the, theta t dot phi. Right? It's just, this is another way to write down the update rule. Okay, so now let's, before I give you the guarantee, let's look at this approach when we no longer assume access to exact gradients. Okay, so now we're kind of cracking open this black box. So it's very related to this question Juan asked about what's the iteration complexity, and I kind of jumped the gun and made it a more challenging question. I asked, what happens when we don't even get exact gradients and when we have to deal with a restricted policy class? Okay, so what are we going to do in this case? We're going to be doing an approximate update rule. We update theta based on an approximate gradient. Just write a little more clearly here. Okay, so we're going to try to do a sample-based approach for this update rule. Okay, an equivalent way to do the sample-based approach is we're just going to do linear regression with samples. Okay, so we literally just run our system with resets. So assume we could do rollouts and we just terminate them at a long enough time. And now we're going to do a linear regression on our data set. That's really the same thing as here, because these SAs are samples we got on the trajectory. And then from that point, we're going to get an estimate of Q by just rolling the system out. And we just do some on policy linear regression, but we're starting from a starting distribution mu. Okay, and that's this coverage aspect. And we'll see, we want to understand the role of having, we want to understand how the choice of mu affects the convergence rates and the accuracy of what we get. Okay, so this is the sample-based approach to do the fit. And our policy update now is uses this, rather than using W star T, it's going to use W hat T, which is the sample-based fit. Again, remember, we're always going to update theta T plus 1 to be theta T minus the sample. This is just an equivalent way to write the update rule. Okay, so this is again, so these two are equivalent ways to write it, but you kind of see what's nice here, because now we're using samples to do this update rule. And now we want to understand how well does this work? Okay, so that's our question. How well does this work when we use samples? Okay, so I'm going to make a stronger assumption here, and then I'll briefly discuss the more general case. So let's suppose that for every policy pi, so Q theta is the one-step look ahead of pi theta. So suppose this is a linear function of our features. Okay, so this is a strong assumption because I'm not assuming approximation error. What we want our features to do is we want them to well approximate every possible value. Okay, so that's assumption 1. Assumption 2, this one's great. This one is one we should be very comfortable with. This is saying that every round, every iteration, we're going to draw enough samples so we have low statistical error. Okay, so we know that epsilon stat, say if we're doing linear regression, we should think about this as being O dimension over number of samples. Right, because we're solving a linear regression problem. The accuracy of solving that linear regression problem with samples is order D over N. So we're going to have error in our updates, but as we draw more samples, the error is going to be small. And the number of samples has nothing to do with the number of states and actions. It's just a polynomial number of samples in the dimension, and we're going to have low on policy risk. So this is literally just low statistical risk. Okay, and the final assumption has to do with properties of mu. And now what we ask is we don't need the starting distribution mu to cover all the states like we did in the exact case. What we need here is we just need coverage in feature space. Okay, and I'll get back to this in the very last slide, that we're not doing exploration here. And what essentially is happening, you can think about this role of mu as a surrogate for exploration. But what's nice here is that we only need our starting distribution to have coverage in a spectral sense over the features. You can even weaken this. So this kappa is we can think of this as a condition number. Just assume our features are bounded by 1. And it's the smallest so it's 1 over the smallest eigenvalue of our feature matrix under the starting distribution. Okay, so as long as our starting distribution has coverage over feature space, which is like the configurations of the system, but not in the high dimensional space of how that, when we map that into this low dimensional D space, then kappa is going to be, that's going to define kappa. And importantly, the main point here is we should think about kappa as a quantity which does not explicitly depend on S and A. Right? And that's the key point here, is that these two assumptions, these two quantities, epsilon and kappa, are quantities which do not explicitly depend on the number of states and actions. Okay? And this is just a modeling assumption. Okay, so now how well does this algorithm work after t iterations? And note each iteration now is relatively cheap because statistically, we can drive epsilon stat to 0 pretty fast. And computationally, we're just solving a linear system with in order d dimensions. Okay, so what's our convergence rate? Okay, so A is the number of actions. We're going to use H to denote the effective horizon. Let's assume a norm bound on the weights. That's, again, analogous to what we do in regression, like a ridge regression sort of assumption. Then after t iterations of this algorithm, we're going to be close to the optimal value function. And we're going to be off by, so now we don't get this fast rate. We're going to be off by 1 over root t, which, so it's a bit slower. But note we have no dependence on the number of states and only a log dependence on the number of actions. Okay, and then poly dependence on H and W, but we should think of H and W as being dimension free. Okay, so we are converging to the right answer after t iterations. And then we get this penalty for having error in our updates. And that penalty is based on a statistical error. And remember that epsilon stat we can think of as d over a number of samples. Okay, but importantly, it's being amplified by this condition number. Okay, because even if we did fit things accurately, it's like, what's going on is basically a distribution mismatch. We're optimizing under one measure, but we want to do well, we're on different policy visits. So even though we might be doing accurate estimates in a statistical on policy sense, we still pay this kappa factor, which is amplified. But if we have reasonable coverage, then things work well. Okay, and again, what's nice here is this is truly an end-to-end statement where we have, we're understanding computational issues, we're understanding statistical issues, and we're getting at global convergence in this non-convex problem. So we're really characterized a set of methods where a gradient-based approach can deal with the curse of dimensionality, and we've addressed computational and statistical approaches in the simplest of cases with where we've assumed this Q function is realizable. Okay, that's often what we call the realizable assumption in machine learning. Okay, so given the time constraints, I won't go into the setting where things are not realizable, but I will. I'm not going to go into details. I'll just say a quick word on this. Okay, so this assumption here is basically saying there's no approximation error if we had infinite data. Okay, in real systems, part of the strengths of machine learning is they're very good at dealing with approximation error. And we might want to understand what happens when there's approximation error. And I'll point you to the paper, but the reason policy gradient methods are effective compared to, say, these approximate dynamic programming approaches is when you look at the more refined theoretical statements dealing with approximation error, they have better dependencies. But it's a lot more subtle because with no approximation error, we already pay this kappa, which we can think of as distribution shift. But with approximation error, the situation is definitely a good bit more subtle. But even there, we're able to characterize some properties of what happens when there's approximation error. But let me just wrap up because I'll just point you to the paper and a book chapter to understand these theorems more generally. Okay, so again, thanks very much for attending. And what I've really been trying to overview is some of the foundations of these policy gradient methods, and that's important because of their fundamental role in achieving state of the art. And in particular, we've been looking at the role of these methods with regards to both optimization and, more importantly, approximation, because that's where they really shine. These methods are very easy to plug in, say, some neural approach and do optimization. And these neural approaches are great for both approximation and generalization. Okay, and we've kind of led up to the point of actually giving you at least one statement with regards to approximation in the high dimensional case. Okay, and there's a lot of new directions here for getting these things to work. So to some extent, we've been assuming in this analysis, I've been assuming we have access to this distribution mu, which has good coverage. And in practice, we need to do exploration. Okay, and another point I'll make is that the theory of RL more generally is different from supervised learning, and I've been kind of writing a book with various people trying to bring forth some of the more machine learning and supervised learning aspects of the way we try to get at generalization. And part of this work is a bunch of these results here, looking at policy gradient methods. Okay, and in the paper, I should also mention, we also treat the neural case. So, okay, and this is joint work with a number of really great colleagues. So Alec has been working with me in RL for a while, and then more recently, been working with Jason Lee at Princeton and Gaurav Mahajan, who's a grad student at UCSD. And yeah, there's a really great set of collaborators. So it's been a pleasure to work with all of them. And to some extent, this is a line of work going on more broadly in the community and over years, just trying to figure out why these incremental classes of methods are more effective with regards to policy optimization. So, so thank you very much. I'm happy to stick around a bit and take some more questions.
Thank you, Sham.
Thanks.
So there are a few questions in the chat box. There's one from Jinfeng Wu asking, can you remind us where the S factor is hidden? Is it hidden in the per step gradient computation? I think this was referring to the last parts of the talk.
Okay, so the question is, where is the S factor hidden?
Yeah.
This is a question with regards to the high dimensional state space, or
I think so. It's yeah, it's the last few slides, I guess. I think.
Okay, good. Let's go back to the formal theorem statement. Okay, so let's go back to supervised learning, right? So we can do image recognition, and we can do this in a way that we don't have to see every possible image in the world, right? So this is basic. So the number of states for image recognition is every possible image that's pixelized. And we can generalize, and we can do this in a way that doesn't depend on the number of states. Okay, and where is the what's the analog of this in the RL setting? Because this is really a question of generalization. Okay, so it's coming up for two reasons here. So we made one assumption that Q theta is realizable. So this means that you can fit a Q function reasonably accurately with a number of samples that has no dependence on the number of states in the world. Okay, so one issue that, so from a statistical perspective, what's happening to avoid this dependence is we have this epsilon stat quantity, but that one I would argue is truly not hidden because we can do regression just like supervised learning. We can use a number of samples that's only order dimension, not the number of states, to get a good approximation to Q. Okay, the other thing that's relevant to avoid this is we need this notion of coverage. But again, this kappa does not explicitly depend on the number of states and actions because that can always be made order D with a well-conditioned basis. Okay, and so part of this is a realizability assumption, which helps us here. But I would argue that assumptions like this, and certainly thinking about the more agnostic setting, this is what we do all the time in supervised learning, because supervised learning, we never talk about the number of possible images. Okay, so that's the statistical part. And computationally, then it's all fine because you're just drawing samples and you're solving linear systems with order D number of parameters. So you actually never need to explicitly write down this policy. You just keep track of thetas, and that is solving linear systems. So it's order D cubed time. So thank you.
Thank you. So there's another question from Renyu Zhang. She was asking, do you have similar equivalence between natural policy gradient and soft policy iteration in the LQR setting?
Yeah, so this is a really nice question. So let me repeat the question. So I'll just make it a little more general. But the question is like, is there a nice relationship between the natural gradient? So here we saw the natural policy gradient was soft policy iteration. Do we have a nice relationship in the LQR setting for how to think about this? Okay, and in the, so I think in the related work, I mentioned one paper with Miriam Fazal, Miran Misbahi, Ranga, and myself, where we do look at global convergence of policy gradient methods. And we actually give two update rules there. So one is a natural gradient-based update rule, and another is, you can really view this as a Gauss-Newton update rule. And both of those two update rules, like the analysis of those update rules are super clean. Like the analysis of gradient descent is really messy. It's definitely simpler than in this case, but it's still like very messy. But once you go to the preconditioned analogs of natural gradient and Gauss-Newton, it's very, very simple. And the short answer is natural gradient is very similar to a soft policy iteration update rule. But there the analog is, you really can just do Gauss-Newton, and that's the soft policy iteration update rule when you have a different step size. And the convergence, the convergence analysis for both of those two cases are very, very simple for the LQR setting. But one point I want to make why the LQR is a little different. See, in an LQR, you truly have curvature in the problem because your objective function is quadratic, and that really does induce some type of curvature in the problem. Whereas here, at the end of the day, it's like we're trying to solve an LP, so we don't have curvature. But I think this is a question I've thought about a fair bit. Like, what's the analog of these methods in soft policy iteration in different settings? So I think it's a really nice question.
Thank you. Oh, and could I ask another quick question? Yeah, so for the natural policy gradient, like we're taking expectations over the stationary distribution that is also kind of like related to our parametrization. So I was wondering like why we're taking, like, is there any additional ways to do policy, to do natural policy gradient, say, probably considering the Fisher information with regard to the stationary distribution? And is there like ways to do that?
Yeah, so this is another nice question. Let me, I'll actually add a little more. Let's go back to, so now I can get into some points about what many people have asked me about. Why is this converging when it's non-convex? Like, is there some convexity in disguise? What's the path we're taking? Okay, so let's go to, here we go. Okay, so the question is about, see what we're doing here is we're taking an expectation over states drawn from basically the stationary distribution. That's where this D is. We start it as 0, we follow it out. So this is the distribution of states we visit. So it's just the analog of the stationary distribution in the discounted case. Okay, and why? So first, the Fisher metric is defined with respect to one distribution. In RL, we have a family of distributions. And we're taking this expectation over states because for every state, right, for every state, we have associated this pi of A given S. Okay, and with that, we have an associated an F theta given S, like a Fisher metric associated with that state. And now we're taking an expectation with respect to states drawn from the stationary distribution. And the question is, why did we choose that? Why not another distribution? So, the short answer is when this was kind of designed, we just chose this station edition. It just seemed like natural, but it also had like interesting mathematical properties that you got this soft policy iteration update rule. And, but at the time, it wasn't clear like why this was a principled approach from, because it was just derived as a heuristic at first, and only later on did we analyze this. So what happens, say, for example, if you use the uniform measure or a different distribution? And, then the question is, maybe like, would you still get the soft policy iteration update rule, or would there be different interpretations? So, so you definitely would not get the soft policy iteration update rule with other metrics. So somehow, because of this measure here, that's what sort of cancels out the measure of where you visit in your gradient, because the gradient is kind of sensitive to where you visit, and you want to cancel out, just because I'm not visiting the last mode state doesn't mean I shouldn't be optimizing there. I really want to boost up, like policy iteration. Just because you don't visit a state often doesn't mean you don't update it. Like, you need to update it there so it back propagates backwards. And if you don't use that, this update rule, this on policy, you won't get the soft policy one. Now, what you might get though is, see, the other question this is leading to is this some convexity in disguise? Because like how, like everyone asks this question, like how are you getting this, like how are we getting this nice global convergence property without convexity? Because we know, like, if we wrote down this MDP as a linear program, that's a convex formulation. Okay, so what we could try to think about is, there's this idea of a state action polytope for solving LPs. So we can write down different variables and try to solve the problem in, a different parameterization. So formally, you could ask, while we're updating theta, could we look at the path of this algorithm, say in terms of Qs or the policies or some variables, to say it's really doing, it's really some type of convex algorithm. We've just parameterized it in some funky way. Okay, and so the answer to Renee's question, so I think if you did mirror descent on the state action polytope, that wouldn't be natural gradient, but that would be like on some different metric. Okay, so so somehow the so there's a lot of there's a lot of relations here, but I think there's a question of once you start warping this distribution, you might be able to get closer to something like doing mirror descent on the state action polytope. But at the end of the day, the problem is once you start doing that, the that algorithm doesn't work as well in practice, and it's not obvious how to implement it either, because we're going to have to keep like changing distributions and such. But I think this is like just more generally a question of how to understand the structure in this problem where things simplify, because we understand plenty of the structure in the convex land through policy iteration, value iteration, and the LP framework. It's just those structures aren't amenable to approximation very easily. But I think just more, so it's a longer answer, but I think I think it's a good question. And because it's a question about what's the underlying, trying to get insights in the underlying structure in this problem. So the short answer, it's subtle, but you definitely don't get these soft updates when you change the distribution.
Thank you.
Thank you. I think there's a few more questions in the chat, but we are way over time. So yeah, maybe we should stop here. And then if there's further questions, you can perhaps contact Sham directly. So we would like to thank Sham again, and thank you all for coming to today's talk. Let's thank Sham again. And next week we'll have Professor Florian Deffler from ETH. So see you guys next week.
Great. Thanks, everyone.
Thank you.
Okay, great. Nice. Thanks a bunch.
Thank you.
Thank you, Sham.